Dr. Azhar, can we start the next session?
Hey, welcome back. Let us start our last session today, titles Emerging Technologies, Electrical Engineering, shared by Dr. Oma Shankar. Let me introduce Dr. Oma. Dr. Oma is Associate Professor in Renewable Energy Lab, College of Engineering at Prince Sultan University. He is working in the field of power electronics, renewable energy, and electrical device. Also is associate editor of IEEE Access. He has author and co-author of many papers related to his field of interests. So welcome, Dr. Oma, as a chair of this session. Okay, so you can start.
Thank you, Dr. Azhar, for this wonderful opportunity in this SMARTTECH 2020 conference as the session chair for the session 8, Emerging Technologies, Electrical Engineering. So I would like to call the authors to present your papers one by one. So I request Mr. Anglip Noor and Saima Ghaffar. Their paper title is Hybrid Image Fusion Method based on Discrete Wavelet Transform, Principal Component Analysis and Guided Filter. So may I request the authors to share their screen and start your session. Are you available? Dr. Azhar, can I call the other next one?
I think we can share the recorded video, Dr. Oma.
Can I invite the next one? Otherwise,
we can share the recorded video because I think let me check, Dr. Oma.
Okay, sure.
Hello, I'm author of the third paper. Can I start?
Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Abid Mir and my co-authors are Andleeb Noor, Saima Ghaffar, MT Hassan, Mir Junaid and Mandeep Kaur. And the topic of our paper is Hybrid Image Fusion Method based on Discrete Wavelet Transform, Principal Component Analysis and Guided Filter. I would like to further introduce my co-authors. Andleeb Noor has done her master's from the Department of Computer Science and Technology, Central University of Punjab, India. Saima Ghaffar has done her master's in Computer Science and Engineering from the Postgraduate Department of Computer Science, University of Kashmir. MT Hassan has done her master's from the Postgraduate
I think the video is interrupted.
University of Kuala Lumpur, Malaysia, and Amandeep Kaur is working in the Department of Computer Science and Technology, Central University of Punjab. Image fusion is defined as a process of combining two or more images into a single image with an extra amount of information present in the fused image and retaining all the important characteristics. Because of the limited depth of focus of optical lenses in charge-coupled devices, it's not possible to have a single image that contains all the information of objects in the image. There are three levels of image fusion: first, pixel level, feature level, and decision level. In the existing work, PCA and DWT-based image fusion methods are used to fuse grayscale medical images, but both of them suffer from inherent drawbacks. To improve the quality of the image without losing the important features and information, discrete wavelet transform based on principal component analysis algorithms can be used as a hybrid approach. So the main aim here is image fusion using discrete wavelet transform and PCA as a hybrid method. The results confirm that the scheme has improved the quality of fused image as compared to existing techniques, but the performance degrades in some noisy images. So there is a requirement to focus on pre-enhancement of images to suppress the noise and enhance the contrast, and then perform image fusion procedure for image quality and enhancement. PCA is a statistical method that converts the number of interrelated variables into the unrelated variables called principal components. Firstly, for both the source images are converted into two or more column vectors depending upon the number of images for fusion procedure. And afterwards, the covariance matrix of the column vectors of source images is being circulated. After the covariance circulation of column vectors, eigenvalues and eigenvectors are calculated from the covariance matrices. And next, the normalization of column vector corresponding to the log eigenvalue by dividing each element with mean of the eigenvalues. After that, normalized eigenvalue acts as the weight value, and then they are multiplied with each pixel of the input images. The final step in PCA method is two scaled matrices that are calculated from previous steps. This added matrix will be the final fused image. This technique is used to reduce the data redundancy. The discrete wavelet transform DWT is a mathematical tool for hierarchically decomposing an image. The DWT provides a compact representation of a signal's frequency component. At every level are obtained two sets of coefficients: approximation, which is LL, and detail, which is HL. This slide gives an overview of the related work and the literature survey that has been performed. And the related work continues here. In PCA method, there is a problem of spatial distortion, and for colored images, there is color distortion. In DWT, the image is divided into high frequency and low frequency coefficients. Due to this, arises of some artifacts and false contour in the fused image. So the proposed method provides better results by removing these problems and producing fused results with high contrast. The hybrid method is based on a discrete wavelet transform and principal component analysis, as has been already discussed, and the flow diagram of proposed method is shown here. So this is the graphical representation of CT MRI fused results. And this is the graphical representation of noisy CT-MRI fused results. The previous methods have some limitations such as spatial distortion, creating artifacts, aliasing, creating noise in the fused image, etc. Also, they have not been used in medical imaging as a hybrid approach. The proposed method overcomes all these problems and provides high contrasted fused images without any loss of information. Guided filter has been used in proposed method to enhance the edge information in the final fused image. After analyzing the visual and statistical results, it is to be concluded that the resultant image obtained from the proposed method has better visual quality and the contrast is high as compared to results obtained from both previous techniques. Also, in performance metrics such as standard deviation, spatial frequency, and entropy of images, there exists a significant improvement. Also, in noisy images, the results obtained with previous methods look same as low contrast image, but results from proposed method are enhanced in contrast as well as their performance metrics shows improved results. Even the proposed method produces a high contrast fused image for low contrast source images.
Thank you so much. So may I invite the next presenter, Dr. Shankar Ganesh, Dr. Jean Jennifer Neeson. High speed, high precision, half precision floating point fused multiply and add unit using DSP boxes.
Good afternoon, sir. Can you hear me, sir? Good afternoon.
Yeah, I can hear you.
Shall I share my screen, sir?
Yeah, sure.
Hello everyone, myself Jean Jennifer Neeson from India, and now I'm going to explain my work paper entitled as High Speed Half Precision Floating Point Fused Multiply and Add Unit using DSP blocks. And first of all, this is a biography of mine, and my co-authors are Dr. Shankar Ganesh and Uma Shankar Subramaniam. And about this paper, first the aim of this paper is a designing of fused multiply and add using half precision floating point arithmetic. And we are here we are using inbuilt DSP blocks for realizing the multiplier and adder. So this DSP blocks here effectively used for fused add multiplier and adder design. And finally, we evaluate our design using image color converting application. So the main aim here, we are eliminating the normalization rounding logic in the multiplier stage to reduce the delay. And this is the main aim of this paper. So we can improve the speed of image color converting application. So the problem statement here is the speed of the design is increased using half precision floating point FMA design. Basically, in existing work, they are using single precision floating point and floating point arithmetic for designing the FMA design. If you go with image processing application, where single precision consume more area because the pixel ranging from 0 to 255. So if you go with single precision, it requires more zeros at the half of the size is filled with zeros only. So computing that zeros, it requires more area and also computation time also increases. So we reduce that computation time using this area effective half precision floating point arithmetic for this FMA design. And this used to speed up the color converting application. And also we use the DSP blocks, and this DSP blocks can perform both multiplier and adder as a single operation. So this is the FPGA DSP block where we have multiplier unit and also the adder unit. So here now adder multiplier output is directly given to the adder output. So in case of discrete floating point arithmetic, we require a normalization rounding at this point, at this multiplier output point. And next, after that only we given that output of this multiplier to this adder logic. But in using this DSP, we directly give the double nth product of this multiplier to the adder logic. We can improve the accuracy also. And considering this computational part of floating point FMA design, it requires 4 different parts. One is sign processing unit, second one is exponent processing unit, third one is Mandisa multiplication and addition unit, and finally normalization and rounding. Before that, we are going to see about the half precision floating point format. And here, 3 different parts. Normally, the floating point requires 3 different parts, one for sign, next one for exponent, and final one for Mandisa. And considering this half precision, the sign bit is equal to 1. Sign uses 1 bit for representing its sign. Positive mean the sign is 0, negative mean the sign is 1 here. And this exponent value uses 5 bit. And this Mandisa, including the hidden bit, the total Mandisa size is 11 bit. And so first we see about the SPU and sign processing unit. So in all cases, we require 2 stages, one for multiplier, other one for adder. So in multiplier stage, the sign processing unit consists of simple XOR gate. So the adder sign of the multiplier input are XOR, and the output is given to the sign computation unit in adder stage. So this sign computation pick the resultant sign by checking the large exponent value, and which operand having the large exponent value, this computation unit consider that sign of that that value is considered as a resultant sign of the entire FMA design. And next one is EPU, exponent processing unit. So here in multiply stage, it uses adder, and this adder used to add the 3 operand, and one is 2 is this EA and EB are the input of that multiplier inputs, exponent of that multiplier inputs, and this again added with the manually calculated 2's complemented bias value. And for half precision, 15 is the biasing value. So we just do the manually do the 2's complement of that 15, and here we add that 15 2's complemented 15 value along with the exponent of the multiplier input. And in adder stage, the exponent comparison is done, and this exponent comparison unit used to pick the large exponent value. Based on that, we align the multiplier input of that multiplier output and also the addend input here. We align this operand of this adder stage for getting the exact result. And the important stage here is MMAU, that is Mandisa multiplication and addition unit. And for this MMAU, we are using the inbuilt DSP blocks. And wherever we have the multiplier and adder in MMAU, we are using the DSP blocks effectively. So this multiplier is 25 cross 18 multiplier, and this adder is 48-bit adder. So this is the FPGA inbuilt DSP block, and this 25 cross 18 we are used to for 11 cross 11 Mandisa multiplier, and this 48-bit adder we are using to add 22-bit 22 double length product of this multiplier and also the another one input. So this is the overall design of FMA design. Finally, we evaluate our FMA design for RGB to Y conversion. And here RGB is the color conversion of red, color image of red, green and blue. And here we are converting this red, green, blue image to Y. And Y having the grayscale of this image, and we can get the black and white image, black and white image as an output. That contains the luminance value of this image, color image, RGB color image. So the conversion equation here is Y is equal to 0.299 into R plus 0.587 into G plus 0.11 into B. So it requires 3 multiplier and 2 adder, and totally it requires 3 DSP blocks. So for each multiplier, it requires 1 DSP block. So entirely it requires 3 DSP blocks to perform that conversion, RGB to Y conversion. And all this multiplier and adder performed with inbuilt DSP blocks. So these are the synthesis result, and we have performed that synthesis using vertex 5 and vertex 7 FPGA family in Xilinx. So these are the synthesis report of each and every unit of this FMA. As we discussed earlier, it contains SPU, sign processing unit, exponent processing unit, Mandisa multiplication and addition unit, finally normalization and rounding. And these are the elements occupied for each and every unit of this FMA. And this is the synthesis result of RGB to Y conversion using this FMA, proposed FMA. And here, this is synthesis results are obtained by giving the 4 lakh test input vector to this FMA design with a range 0 to 255, that representing the image pixel value, and 4 lakh test vector we are using to evaluate this result, and power is calculated using VCD file, value change term file. By generating that is a switching activity stored file, and that switching activity calculate the power of different types of input. So it 4 lakh input, 4 lakh test vector can provide more switching activity information about that FMA design, so we can get the accurate power values. And also the delay is calculated from input to each output, and that is in a nanosecond value. So we can optimize all this value using our inbuilt FMA based, DSP based FMA design. And finally we compare our result with the existing work, and we will get the optimized result. And this optimization performed with eliminating the multiplier stage, normalization, rounding logic, and also in adder stage we perform the truncation. For rounding we perform the truncation instead of doing rounding to nearest even rounding logic. That is the exact method for getting the perfect result. But in this case we have some error, but the error level is very acceptable. But doing this truncation, we eliminate the unwanted LSB bits, and we take only the MSB bit with the size equal to the Mandisa size of the half precision floating point arithmetic. And this is also used to save the area, and also mainly it is used to speed up the entire design for color converting application. And these are the results we obtain. We tabulate the result in this table. And these are the works we performed for color converting application using our proposed FMA design. Thank you.
Thank you so much for your presentation. So I request the audience, any questions? Any questions from the participants? If there is no questions, can we move on to the next?
Hello, can you hear me?
Yes.
Yes.
Okay. Can I share my presentation?
Thank you, sir.
Can I share my presentation? Sir, can I share my presentation?
Okay, next participant. So okay, I will wait. I will introduce to you. So the next presenter for this session is Mohammad Ishaq and Mohammad Hamad Afzal. The title of the paper is Supervised Machine Learning Based Artificial Neural Network Approach for the Control of Matrix Converter. So now I welcome the author to present.
Hello, can everybody listen? Hear me?
Your voice is not audible. Can you increase the volume?
Actually, maybe the internet connection is not good. Volume is full. Can you hear me now? It's
Yeah, could
100%.
you please say loudly? Like it could be better.
Okay. The paper which I am going to present is supervised machine learning based artificial neural network approach for the control of matrix converter. First of all, these are my table of contents. Problem statement, matrix converter. I will go with the definition of matrix converter and all its attributes. Then the control topologies which have been used for matrix converter, the matrix converter control techniques, a bit of literature review, then the ANN control, and after that ANN training, then I will present my simulation result, and at the end I will give conclusion and references. Now, why we need a novel technique for the control of matrix converter? This is because the current control schemes of matrix converter do not respond very effectively to the changes in the loads. When the load changes, then the matrix converter control is not efficient. The changes in the load requires the model of the system to be changed. Therefore, neural networks are being used as these are based on data and they're presenting an opportunity to be used in the control for the matrix converter. And we have implemented this technique. Now let me introduce the matrix converter to you. The matrix converter is basically a direct AC to AC converter. It has no intermediate DC link capacitors. It is producing sinusoidal waveforms at the output. It is operating at almost unity power factor. It can be used to control reactive power of the system. It has bidirectional switches and it also supports regeneration. There are mainly two basic matrix converter types. One is direct and the other is indirect. The direct matrix converter can be seen here in this figure where there are inputs and outputs 3 and 3. While the indirect matrix converter has a bit of change, it has a virtual DC link capacitor here at points P and N, and it has these switches which are further reduced through a mechanism into 9 as we have 3 inputs and 3 outputs. There are different topologies which have been used for the matrix converter. As I already mentioned, bidirectional switches are used in matrix converter that can be configured in many ways for the creation of topologies. The choice of a certain topology is purely dependent upon the application. For example, in few application, you would need 3x3 matrix converter. In few, we would need 3x4. Similarly, 3x5, 3x6, or 3x2x3 matrix converter. Now, what are basically these 3x3? Actually, these are showing the inputs and the output. For example, in 3x5 matrix converter, we will have 3 input phases and 5 output phases. Similarly, each topology has its own attributes and is used for specific application. Now, the conventional control techniques of matrix converter are space vector control, scalar control, predictive control, and torque control. However, these control techniques have certain shortcomings. Like these topologies require different control techniques. The control technique further depend on the type of application or load. In this figure, we can see that the dotted line is an ideal one, and the other are for the control techniques. For example, this blue one is for certain specific control techniques as the and it is showing the response of a load. For example, if the load changes, then the ideally it should be like the dotted line, but it don't remains like the dotted one and it changes like the red one and even the orange one. The output deteriorates, which is not required. Therefore, the system must be very efficient in detecting the response at the load and it should adjust accordingly. Here's a brief literature review. In the first paper which I've selected, double start induction motor is fed by matrix converter. The matrix converter is controlled by space vector modulation and speed of DSM is regulated by adaptive neurofuzzy inference control. Result shows that there is an overshoot elimination and robust control. Complex calculation of direct power control are replaced by an NN system that uses individual training scheme with fixed weight and supervised models. And the next paper, selection of fitting factors and multi-parameter predictive control in is manual and exhaustive process. It is conventionally determined using trial and error method. The paper is also automating the process of selection of fitting factors through the use of artificial neural networks. In the next paper, dual stator induction motor is controlled using direct power control method. The DSIM is then driven by the indirect matrix converter, and the indirect matrix converter is then modulated through neural network control. The research has shown that it offers enhanced flux, power, and speed control. In the next paper, radial basis function neural network was used for driving the power converter. The research is also offering instantaneous power tracking, voltage regulation, and voltage balancing. Now I'll come towards the artificial neural network control of matrix converter. Basically, there have been two types of ANN control techniques that I've included in this paper. One is the ANN control based on the data which was obtained from predictive current control in the previous. It is also based on my previous work. And in the second technique, I've used random data for the control through ANN. As I already mentioned, in the second ANN method, no data is obtained from previous control techniques. Instead, all the data is randomly generated. The benefit of randomly generation of the data is that the model is not biased toward any particular load, and it can effectively cope up with the change in load. And when such model is fully trained, it will be able to recognize the different patterns that are being seen in the loads. This diagram shows the basic block diagram. We have three-phase input, three-phase source, and then there is an input filter which is fed to the matrix converter, and the matrix converter is connected into load. This is where the references are given: reference current, reference voltage, and the load, and which is then fed into the cost minimization function. And based on the cost minimization function, switching state is being selected, which is then fed into matrix converter for the optimum switching state selection, and then then the system is working accordingly. In this slide, the training results are shown for ANN method. And these results are basically for 3x3 matrix converter. As in 3x3 matrix converter, there are total number of switches are 27. However, only 15 of them are being used. The main diagonal entries in the left figure are showing that the model is able to recognize with many high percentage, mostly above 95. Like you can see that for the switching state number 1, if the switching state is also number 1 and predicted class is also number 1, then the result is 98%. However, if the switching is 1 and the predicted class is 22, then the result is 1%. Therefore, the diagonal entries are showing the best suited results, which is almost 98 and 99%, and at some level there are 97%. However, the right figure is showing the receiver operating characteristic curve, which is RC curve for the first of the ANN model. The first ANN model was based on the model predictive control data, which has been acquired already. The score of the model lies at 0.01 and 0.98, which is showing that the false positive rate is 0.1 and the true positive rate is 0.98, which is showing a good classification. This slide is about in the top figure. In this figure, it is showing that the cross entropy curve of the ANN model based on the random data, and the best performance is obtained at epoch 500. When the probability of the prediction is increasing, the cross entropy is decreasing rapidly. The lower figure is showing that there is one hidden layer and one output layer. The output layer is being obtained through transit function, as already mentioned, whereas the output layer is deciding its functionality through softmax function. Here are the simulation results. The results are for the random data of artificial neural network control for 3 cross 3, 3 cross 4, 3 cross 5, and 3 cross 6 matrix converter. The left column is showing the input current and right column is showing the output current. It can be seen that the output waveform of the current is quite sinusoidal. This slide is regarding the output current waveform for 3 different loads. The figure A is showing the performance of the first ANN method where the data was already taken from the previously implemented technique, model predictive current control technique. This shows the performance of the its performance is good when the load is similar to the training model. Like when you train the model based on the present data, as the performance of this model is very good. As you can see, the dotted is of ideal one and the blue one is of the performed data, while the other two waveforms are required when the load is a bit changed. However, when you compare it to the B, which is being acquired, which is the result of ANN model, which was trained on random data, the result is quite satisfactory. It can be seen that the performance of the system is not deteriorating as much as seen in the model which has been trained on the model predictive current control data. So it can be stated that if the model is trained by random data, it is very responsive to the change in load and it adjusts itself and the output is is not deteriorated. So it can be concluded in overview of the matrix converter and with its type and topology and control techniques was given in this paper. An ANN control algorithm was presented and it has been used for the control of various topologies of matrix converters. Two models of ANN control were created in MATLAB. As I already mentioned, one was for the random data and the other one was for the already acquired data from the previously implemented technique. The first model was trained using predictive control data and the other was on the random data. Using this NN method, the output current of matrix converter remained stable even if the load was changed. Here is the list of few references. Thank you. If you have any questions, you may ask.
Thank you so much for your presentation. I have a question like, so do you have any results of comparison with the existing researchers?
For the existing results of which
technique? Existing research papers.
Actually,
you compare?
Actually, I was not able to find any specific paper which was relevant to the work that I have done.
Because you have taken the literature review, so why not you compare your results, existing literature results, so that you can claim your results?
Sir, that's what I stated, that actually the work which I was performing for the control of matrix converter in achieving its results was quite different from the other one. That's why I haven't compared it yet.
Okay. So any other questions from the participants?
I have a question.
Yes, sure.
Yes, please.
Yeah, so I have just two separate questions. First is, in your block diagram, you are using a low pass filter in the input side. So what is that purpose? Why don't you use it at the output side of the converter where you are connecting with the load? Secondly, the load is changing continuously, so it sounds more like a regression problem rather than a classification problem. Why have you preferred classification? So what is the base behind it?
Actually, for your first question, the input filter was used for removing the noise in the signal.
So why haven't you used it at the output as well, at the other side? What is the value of the I3 load you are using to train your neural networks? Is it the output of the filter or the output of the matrix converter?
It's because of the output of the matrix converter.
the matrix converter, output of the matrix converter. So don't you think there will be a noise at the output of the matrix converter as well?
No, there is no noise at the output of the matrix converter, but at the input there is noise, and for reducing the TSD, it has been used.
Hello?
Hello, are you
You have to
satisfied with the
share your
answer?
screen. I can't see the screen.
Okay.
I think that's fine. Maybe you can give the clarification as of now.
Yeah, sure.
Sorry, I'm not able to hear both of you properly. You want me to share screen or like what?
It's up to the moderator.
Yeah, you can share the screen. No issue.
Are you able to see the screen?
Yeah.
Yes. In my block diagram?
Yeah, in your block then.
Yes.
Yeah, so what is why don't
As
you
I've
use the filter out?
as I've already mentioned that the input filter has been used for reducing the noise in the signal. While at output, the filter is not required because there is not much distortion and the TSD has been like optimally reduced. I haven't included the pictures of THD because I thought it would not be necessary for this, but at output THD is quite low.
All right, but okay. And lastly, why classification? Why not regression?
Sorry?
Because the problem sounds more like a regression problem to me. You are trying to approximate a function, right? Because the load is varying and you want to find a
Actually,
function between it.
your voice is coming too hard at me that I'm not able to understand. Let me reduce the volume.
I will ask the same question. Why not you use the regression instead of classification? Because classification mostly they use to identify different case.
Okay, why I used classification but not regression? The answer to this question is that because there are only 27 states that have been used in the matrix converter when you come to 3x3 matrix converter. So regression regression is not required.
But the problem statement says it requires the regression, not the classification.
Sorry?
The problem statements, I understood from the problem statement, it needs a regression instead of the classification, because here you are not going to classify any fault or any different case studies. Okay, so you're just going to use the control method to remove the noise. That's it.
Actually, I'm not able to understand your question at the moment because I'm not able to understand what you mean that why I have not used regression but classification. As I already mentioned that I have not used regression because of the states of the matrix converters. Like there were only 27 states of the matrix converter that I have been using.
Okay then. So any other question from the participants?
Yeah, I can ask one last question if it is possible.
Yes, sure.
Yes, please.
Yeah, so you said random data, but the data that I can see is just a sine wave with some noise in it. So is it just random data? If you go to your slide 11,
slide 11,
you go to your slide 11. Yeah, so you can easily see that it's just a sine wave with some noise in it, right? So can you classify it as random data? Yeah, can you classify it as random data? Do you think it's random?
Sorry.
Can the moderator repeat my question? Maybe he's not hearing me clear.
Actually, yeah, this is the first waveform is looking like it's not a random data. Okay.
Actually, is you want to ask that this is not looking like a random data but a sine wave.
Yeah, especially the input current.
Actually, random data for the training of matrix converter is the same.
Okay, so what does it mean by random data? That's the question.
Sorry, I will not be able to answer your question.
No, in your title you have used the random, something like that. So what does it mean by random?
Actually, I'm not able to answer you at the moment. If you can leave your email address, I'll give you a detailed answer.
Okay, then no issues. So if there are no other questions, I think thank you so much for your presentation. So I hope so. This session is over. I will hand over to the conference organizers. Thank you.
Thank you, Dr. Omar, for sharing this session, for nice session presentation. I'd like to thank you so much. It is well organized, very interesting. Thank you. Really, this was the last session in our second day of SMARTTECH 2020. Let me thank all participants and presenters and the session chairs for attending the second day of SMARTTECH 2020. And see you tomorrow, inshallah, to celebrate with the Best Research Paper Award and the Student Paper Awards. So I hope to see all of you tomorrow for the third day of SMARTTECH 2020. Thank you so much and have a nice day. See you tomorrow, inshallah. Thank you.
Thank you, everyone.